morning. The last two classes we have been discussing cosmological distances. Today and in the last class I told you that supernova of type 1a are very good distance indicators. They are extremely bright, so you can make them out in distant galaxies. I told you that these are accreting white dwarfs, and in the process of accretion the mass, when it crosses the Chandrasekhar limit, you have the supernova of type 1a. That is what is believed to happen. These stars, these supernova of type 1a, unlike other supernova, occur in old stars of mass around 1 solar mass. These are white dwarfs, so masses of the order of 1 solar mass. So such stars occur in both ellipticals and spirals. So you are not restricted to only spiral other supernova. Many other types of supernova occur only in the massive, very massive stars. So you are restricted to spiral galaxies, whereas supernova of type 1a occur in both ellipticals and spirals. So you are not restricted that way. Now the properties of these supernova are quite uniform across the entire supernova sample. This is not true for supernova of type 1b or type 2, etc. So this was the picture I had shown you in the last class. This is the supernova 1994D. Now these supernovas have a characteristic light curve. The radiation increases and then it is roughly constant for some time, and then it decays over a period of around 30 days. And the increase is essentially because there is a gas envelope which is ejected when the supernova occurs, and that is expanding. I had explained this in the last class. As the radius goes up, the luminosity increases. Typically it is because of this reason. So this picture, these pictures here show you the light curves of the supernova 1994D. So what is shown over here is the magnitude along the y axis. You have the observed magnitude. Along the x axis you have the time in days, Julian days. Okay, so in days. So this is the time in days and this is the magnitude. I have told you what we mean by magnitude in the last class. So when the magnitude decreases, the luminosity, the flux goes up, right. So let us take a closer look at these light curves. So these are the light curves of the supernova 1994D. And I had introduced various bands, photometric bands, in the last class. So these are the light curves in the different bands, U, B, V, R, etc. So there are 6 bands for which the light curves are shown over here. On this axis is the magnitude. You can see that the magnitude is decreasing upwards along this graph. So the flux goes up, then there is a plateau, and then it falls. And this whole thing, if you look at the y axis, it is over tens of days, more than a couple of tens of days, okay, of the order of tens of days. So this is, and you see this similar kind of thing occurring at all the bands, though here it is different. Okay. So this is what we mean by the light curve of a supernova. It shows you the flux coming from the supernova as a function of time. Now one possibility people first considered was to use the peak luminosity, maximum luminosity. So as the supernova explosion after the supernova explosion, the luminosity goes up, and people had thought that this could be used as a standard candle, the peak luminosity. So, it was believed that this is constant across the entire supernova 1A sample. But later on it was found that this does not work as a very good standard candle, and there are considerable differences. So, there are supernovas for which the peak luminosity differs quite a bit. It is not that it is the same for all supernova of type 1A. So, this is not a very good standard candle if you use the maximum luminosity. It was found that the shape of the light curve has very interesting correlations, and these correlations in the shape of the light curve allow the supernova to be used as very good distance indicators. Okay, so, the use of supernova of type 1A as distance indicators rests on the fact that the light curve of these supernova are well correlated with different properties of the supernova. So, I am going to here discuss only one of these. So, the supernova, the shape of the supernova light curve is correlated to the luminosity, and this is a picture which exhibits that, where you can see this. So, in this graph, so you have to be careful how you read these graphs. The previous graph had the magnitude. Now, this graph has the absolute magnitude plotted along the y axis, and this is the time in days. Okay. Now, in this graph, the magnitude is going down as you go up, does not increase, it decreases because there is a negative value and it is a larger negative value as you go up. So, the curves on top are for intrinsically. So, the fact that you have absolute magnitude, the previous graph showed you the apparent magnitude, it is a flux. This graph shows you the absolute magnitude, which means that we have corrected for the distances. So, we somehow know the distances to these supernova, and we have corrected for that, brought it to a distance of 10 parsec. So, calculate the flux if the supernova were at 10 parsec. So, now you can compare the magnitude from different supernova. It is just the luminosity, representative of the luminosity, and the graphs on top are the more luminous ones. They have a smaller absolute magnitude. Minus 20 is brighter than minus 15 or minus 10. Okay. So, the ones on top are the brightest supernovas, the ones at the bottom are the faintest supernova of type 1A. And what you see is that after the maxima, the brighter supernova, the more luminous ones, the light curve falls much slower as compared to the faint ones. The faint one decays much faster. So, the brighter the more luminous the supernova, the slower the light curve falls. Okay, the slower the light curve falls, and this was a very important finding in the mid 90s, early 90s, mid 90s. And it was found that the shape of the light curve is not only related to the luminosity, but it is also related, there are other properties of the light curve which are related to different properties of the supernova. Okay. And all of these tight correlations allow us to use the supernova as a standard candle. So, if you use this property, if you can measure the rate at which if you can determine this whole light curve, then you can fit it to these samples, see which one it matches. If you try to match it with a one that is a little too faint, you will find that the faint one decays much faster. If you try to match it with one that is too bright, you will find that it decays too slow. There will be only one or a range where it matches. Okay. And once you know to which one it matches, you can determine the luminosity of the supernova. So essentially, by measuring the light curve, the shape is unique, you can determine the luminosity. Okay. So these correlations are also referred to as the magic of the supernova light curve. So you can use these supernova light curves to determine the luminosity of the supernova, predict the luminosity. And once you know the luminosity and you can measure, so from the shape you can predict the luminosity, the peak luminosity, and you can actually measure the flux. So in terms of magnitude, you can measure the apparent magnitude of the peak, you can predict the absolute magnitude of the peak from the shape of the curve. So you know both of these. Once you know both of these, you can predict the distance. Okay. Now how to test this? Is this correct or wrong? Okay. So this shows you a Hubble diagram. Now recollect the Hubble diagram that we had discussed earlier. Look like this. It had distance and velocity plotted, right. Now this has been replaced by this kind of a Hubble diagram now, this kind of a Hubble diagram. So let us spend a little time just discussing what this Hubble diagram tells us. So along the x axis we have the redshift, and it is plotted here in logarithmic intervals. Okay. Along the y axis we have the difference in magnitude between the apparent magnitude and the absolute magnitude, and this difference in magnitude I had told you is the distance modulus, right. So forgetting about the k correction and such things have been put in, so forgetting about them, let us assume that they have been taken care of. This is 5 log base 10 d, the distance to the supernova in to the object in general in units of 10 parsec. So if you know this, what you get is essentially 5 log the distance. And in the nearby universe, the distance is Cz by h naught. So if you plot a graph of the distance modulus versus log z, you expect it to be a straight line in the nearby universe. So this is true when z is much less than 1, and this will be true only if this will be a straight line only if the absolute magnitudes predicted by you using these relation between the shape and the luminosity, this will be a straight line only if these graphs, this is correct. So this is a test that this indeed is a good standard candle. The observed distance modulus, distance moduli, plotted as a function of the redshift in logarithmic intervals, data taken by different groups of observers, all of this data is found to lie on a straight line. Okay. And this goes up to a redshift of around 0.2, up to 0.2. Okay, this is low redshift. Now there is a point which you have to note over here, the point is that the calibration of this curve depends on other distance indicators. After all, from the apparent magnitude to determine the absolute magnitude, you need to know the distance to the supernova to calibrate these curves, to get these curves. So, the calibration of these curves depends on other distance indicators, okay. And there are uncertainties in these other distance indicators. So, you can in principle use this graph to determine the Hubble parameter. That is the only other free parameter in this, right, that is the only other free parameter. But the whole thing now depends on the how well you have calibrated these curves. Okay, so that is the issue. So this does not independently, this tells you the Hubble parameter provided you have calibrated these curves correctly. If the calibration changes, what is going to happen is that all of these curves are going to move up or down. Okay. So this is the low redshift sample of supernova. It allows us to test the question how good a standard candle are these supernova type 1a. Now, if you go to high redshifts, this relation no longer holds. We have discussed this in earlier classes, and you have to now calculate the luminosity distance for different cosmological models, and the distance modulus is now dependent on which cosmological model you are working with. And this graph, so up to a redshift of around 0.1, 0.2, all of them are the same, but as you go to higher redshifts, so in this range they are all the same, redshifts less than 1, but as you go to higher redshifts, what you find is that there are deviations, and these deviations depend on which differ depending on which cosmological model you choose. Okay. We are going to discuss cosmological models which are parametrized by just 3 parameters. I have discussed these models, class of models earlier. So, we are going to discuss a class of cosmological models which are parametrized, whose late time evolution, you see the supernova can only probe the late time dynamics. Supernova observations do not go to redshift of hundreds and thousands, they are restricted up to order of unity. So, we shall be discussing cosmological models where at redshifts of order unity the expansion can be described, quantified using just 3 parameters. These 3 parameters, so the Hubble parameter as a function of the scale factor in these models is given by h naught, omega matter naught a to the power minus 3 plus omega curvature naught a to the power minus 2 plus omega lambda naught. And omega matter naught plus omega curvature naught plus omega lambda naught, omega lambda is a constant actually, so the 1 is not essential, the sum has to be 1. So, only any 2 of these parameters along with the Hubble parameter, which I have already discussed in the last class, 2 classes ago. So, they completely tell you everything about the expansion history, and only 2 of these parameters are independent, the third one is fixed by the fact that the sum has to be 1. So, we shall be treating with this, we shall treat these 2 as the independent parameters. The curvature, omega curvature is determined by these 2 values. And bear in mind that if omega curvature is 0, it is a flat model, k equal to 0, flat. If this is greater than 0, it implies that the constant k that appears in the FRW metric is less than 0. This is the open model, negative curvature, and if this is less than 0, omega curvature is less than 0, oh this is sorry, k equal to minus 1, actually k can have k equal to minus 1, and this is the model with k equal to plus 1. This is the closed model. This is the model where the spatial space has a constant positive curvature, so the universe is closed, it is a 3-dimensional sphere. Okay. So, omega curvature is not an explicit parameter here, it is determined by these two parameters, and it determines the geometry of the space. It is related to the geometry of the space in this fashion. So, these graphs show you the distance modulus for different choice of these parameters omega matter and omega lambda, and the shape of these graphs over here depend on the choice of the parameters, choice of these two parameters. It also depends on the value of H naught. Okay. Now, what is plotted below is something slightly different. Let me explain to you what is plotted below. What is plotted below is the difference in the distance modulus. And what is meant by this is that this is the difference in the distance modulus in the model that you are considering and the model where both omega matter and omega lambda are 0. So, if both omega matter and omega lambda are 0, if both of these are 0, omega curvature is exactly equal to 1, there is no matter. We have discussed this model. This is the model where there is no gravity. So, the scale factor is a linear function of time. Right? If the universe were expanding freely, this is what you would have. Okay. And here omega curvature is positive, so it is the open model of negative spatial curvature. Okay. So, it is a difference in the distance modulus of these two models, the one that you are considering and this model. Now, a feature here you see is that if you calculate the distance modulus, it has a dependence on the Hubble parameter in addition to the cosmological parameters, right. When you calculate the distance modulus, the luminosity distance, that depends on the Hubble parameter and these parameters. Okay. Now, when I take this difference in the absolute in the distance modulus, the Hubble parameter dependence cancels out. When I take log, multiplying by a constant means adding a constant. So, when I subtract these two, the Hubble parameter dependence cancels out. So, this is something that depends only on the cosmological parameters. It does not depend on the Hubble parameters, value of the Hubble parameter. Okay. Another way of thinking of this is that it is the ratio of the flux of the distances in these two cosmological models, the one that you are considering and the one this with no matter and cosmological constant, no matter, no cosmological, is the ratio of the distances. Okay. So, this is the quantity that is plotted along the y axis, and along the x axis we have the redshift. So, it is exactly the same graphs that I had shown you earlier, just plotted in a different way. Okay. I had shown you graphs for dl, the luminosity distance as a function of redshift. It is exactly few classes ago, it is exactly the same graph, just plotted in a different way, that is all. Okay. So, these are the different models that are shown in this graph. So, the model, the graph, the curve shown on top. Okay, first this is the straight line, the horizontal straight line is the one where the omega is 0. That is obvious, right, because if this matches with this, it will not be a function of redshift. So, the horizontal straight line is the one where there is no matter, no cosmological constant, all curvature, freely expanding. Okay. Now, the upper graph, the topmost graph is one where omega matter is 0.3 and omega lambda is 0.7. That is the topmost graph. Okay. And the one over here has omega matter 0.3 and omega curvature 0.7. And recollect that we had looked at the luminosity distance for these two models, and we had found that the luminosity distance for the model with omega matter 0.3, omega lambda 0.7 was more than the curvature model at low redshifts, till a redshift of around 3, beyond which this model predictions are larger, which is what you see here also. The distance modulus is more till a redshift of around 3, beyond which the distance modulus of this model with curvature overtakes it, but that is not shown on this graph, that region. Okay. So, just to make this point clear, let me just show you the picture. Let me just show you the picture, it will just take a few minutes. So, this was the graph that I was referring to. So, these were all the models that we had considered, exactly the same thing, except the one with both of these 0 was not there. Okay. And the luminosity distance, look at it on this scale. The upper one is the one with cosmological constant 0.7, the lower one is with cosmological constant 0. Okay. So, you see that at a redshift of up to 3 roughly, the LCDM model predictions are higher. After that, that falls and the open CDM model goes up. Okay. The LCDM is omega matter 0.3, omega cosmological constant 0.7, and this has 0.3, 0.7 for curvature. So, these graphs and this graph is exactly the same information is contained in both of these. Okay, exactly the same information. Now, this shows you the supernova data being compared against these graphs. So, the low redshift supernova up to a redshift of 0.1 is unable to distinguish between these models. So, they are all, these are the errors in the measurements. Okay. So, the low redshift supernova data are all the same for all the models. Now, when you put in the high redshift data, so this is the high redshift data, the original high redshift data, you see that there is a possibility that you can distinguish between these. So, this is the model with total omega 0, this is the model with omega matter 0.3, omega lambda 0.7, this is the model with omega matter 0.3, omega lambda 0, this is the model with only omega lambda. Okay, the distances go up much faster. Now, if you bin these, so the data actually, there are a large number of supernova at the same redshift, because you can observe supernova all over the sky. So, you have in these observations, you have a large amount of data at the same redshift or in redshift intervals, and the supernova data extends all the way up to redshift of 1 and slightly more. Okay. So, and these individual data have reasonable errors. So, you cannot, from one supernova data, you really cannot say which of these is the favored model, but you can bin the data. So, these what this is that they have binned the median distance modulus in some bin in redshift. So, you have combined all the data. If you combine a large number of independent data, the error goes down as the square root of the number of data points that you have combined. Okay, so, the errors have gone down, and this gives you the possibility of discriminating between different cosmological models. Okay. So, this is more supernova. This is data from 209 supernova, and the data has been binned. So, you have the medians in different redshift range, and it extends up to a redshift slightly more than 1, and you can see that it favors the model with omega matter 0.3, omega lambda 0.7. The model with omega matter 0.3, omega lambda 0 is the curve in between, and the model with only omega matter equal to 1 is the lowest curve. They are not, they are disfavored. Okay. The way these results are represented is what is shown over here. So, you have these two parameters which completely parameterize the dynamics of the expanding universe in these models. H naught is just a constant which does not come into the picture here. So, you have these two parameters, omega matter and omega lambda. Omega matter here is omega matter naught, present value. Okay. So, you have these two parameters, and they could a priori, I mean, to start with, they could have any value, we do not know. Okay. Now, the question is what value of these omega matter and omega lambda is consistent with the supernova data, or other way around is that what values of these parameters are allowed. Okay. So, what does the supernova data is going to tell us what are the values corresponding to our universe. Okay. So, that is what is shown in this graph. So, these curves over here are the intervals, they are the confidence intervals. So, we can say with 68.5% confidence that the value of omega matter and omega lambda, which gives a fit to the supernova data, is of our. So, if the supernova data is correct, the omega matter and omega lambda that of our universe with 68.5% confidence, we can say that it should lie within this curve. Okay. And with 95% confidence, we can say that it should lie within this curve, and with 99% confidence, we can say that it should lie within this curve. And there are different data groups which have done independent observations. So, they have different confidence intervals depending on their data. Okay. And these data are of the late 90s. So, in the late 90s, it was possible to start putting restrictions on the allowed values of these cosmological constant parameters omega matter and omega lambda. And the supernova data seem to indicate at a reasonably high level of confidence that there is some omega lambda. So, omega lambda has this property that the pressure is negative, right. So, the supernova data was already indicating that at a reasonable level of confidence the universe has some omega lambda. You require some component omega lambda. Yes. not 0. Okay. Prior to that, people thought that we live in a universe where omega matter is 1, spatially flat, and nothing else is there, omega matter 1. Okay. But with the supernova data, advent of the supernova data, actually even before that, it became evident that omega matter alone, ordinary matter alone is not adequate to explain the expansion history of the universe. You require some cosmological constant or something like that, something that has negative pressure. Okay. So the value of these parameters were required to lie in this range with these different levels of confidence. Now there are other curves on this parameter space, so let me explain that. We have seen that if the universe has only a cosmological constant, there is no Big Bang, it expands forever. Whereas if there is a matter, if the universe has matter, no cosmological constant, then there is a Big Bang. So there will be some transition between these two, there will be some value of omega matter and omega lambda, beyond which we will have a Big Bang, and on the other side we won't. So this is the curve shown over here. Okay, so these points, there never was a Big Bang, they have very high values of omega lambda, so that the Big Bang never occurs. We have actually worked out explicitly when omega matter is 0, we have worked it out, and this omega lambda is 1, we have worked out the expansion history, we get an exponential, but it is not only for this point, all of these points you do not have a Big Bang. Okay. Now we have further seen that the value of omega curvature determines whether the universe is spatially closed or flat or open, right. So this is the value where omega curvature is positive or negative is decided by this line over here. So if omega lambda is 1, then omega curvature is 0. If omega matter is 1, then also the omega curvature is 0, or if omega matter is 2 and this is -1 again. So there is a line over here. To the on top of this you will require a negative omega curvature, or the k has to be positive. Below this, a positive omega curvature, or k has to be negative. So these are the closed models, these are the open models. Okay, these are closed, spherical, these are open, and this line is the flat. So you see that the chances of getting a flat model are extremely small if you just think of it as terms of pure random. So you choose a point on this at random, parameters value at random, the chance that it is spatially flat, the universe is spatially flat, is extremely small because the point has to lie on this line. Okay. So we have seen that there are these regions where the beyond here the universe is spatially open, here it is flat, and this is this line is flat and here it is closed. Now we have also seen that the value of omega curvature determines whether there is going to be a big crunch or not. Big crunch may mean that the universe is going to collapse again or not. And if omega curvature is negative, the universe is going to collapse again. This we have studied right in the beginning. If omega curvature is positive, it is going to keep on expanding forever. Now if you put in a cosmological constant, then this gets modified, and this is the graph, this line here is the demarcation in the region between where the universe is going to expand forever or if it is going to collapse. And this line over here demarcates the region where the universe is accelerating at present, or it is if it is deaccelerating at present. This again is an issue that we have discussed. If I have a matter dominated universe now, no pressure, the universe is expected to be deaccelerating. If I have a cosmological constant dominated universe, the universe is expected to be accelerating, right. So this is the, if you put in curvature also, this is the curve that demarcates these regions. Now this is later data So, all of this data has been combined supernova. So, the more the data, the less the errors, the small, because you are combining more and more independent observations. So, the errors are small, and the errors in the observations are essentially what are reflected in these confidence intervals. Smaller the errors, with better precision you can pin down the parameters. Okay. So, this is the allowed parameter range, 68.5% confidence level, 95, 99% confidence level. You can say that the parameters values for our universe lie within these contours. Okay. And we can say with a reasonably high level of confidence that there is some lambda. So, there is some term, some constituent of the universe which has negative pressure. Okay, this is the supernova data. So, essentially it is a distance measure, and by measuring the distance, luminosity distance as a function of redshift, you can pin down the values of the cosmological parameters. There are other cosmological observations about which I shall discuss later. So, there are observations from galaxy redshift surveys, and these observations from galaxy redshift surveys, they tell us what the value of omega matter is, present value of omega matter is, and these observations, they pin down the value of omega matter in this range 0.2, 0.3, somewhere over here. They do not put any restriction on the value of omega lambda. Okay. This has to do with the growth of perturbations. How you, if you put a, okay, we will come to this later. There are also observations of the anisotropies in the cosmic microwave background radiation, essentially, okay, of again this is the angular diameter distance. This again, that is something I shall discuss. So, they also, the interpretation of these observations also depends on the cosmological parameters, and they restrict the parameters to this region. So, all of these together tell us that the values of omega matter and omega lambda, they should lie somewhere in this range, somewhere around 0.3 and 0.7, omega matter 0.3, omega lambda 0.7. Okay. So, in summary, a model for the universe parametrized in terms of these three things seems to give a reasonably good fit, and if you accept this parametrization, then the values of the parameters corresponding to our universe lie somewhere over here. And this is one of the big issues in present day cosmology, to determine the parameters of our universe at a great level of precision. It is called precision cosmology. Okay. These are names that have been given. Now, the question arises, what is this dark energy? By dark energy, we refer to this term over here. Remember that this term is essentially parameterized in something that has negative pressure. Okay. And how do we know that this term is there? Let me just briefly go back and right. How do we know that this term is there? How do we know that this term exists? We know that such a term has to be there because if you do not have this, we know that omega matter is 0.3. Okay. Suppose you accept this, omega matter is 0.3, and we say that this term is not there, then the rest of it has to be curvature. Okay. Then the distance modulus should be like this. Okay. Or the distances should be smaller than what you actually see. The distance modulus being lower means that the distance is smaller. Okay. The distance modulus being larger means that the distance is larger. So, the supernova, if you had this model, the supernova would appear brighter. okay, you would then predict a smaller distance and this model would be consistent. If you had a model with only omega matter 1, then the distances should be even smaller. Okay, so the supernova should be even brighter. So at the same redshift, I observe the supernova. If I am in a model with omega matter 1, then the supernova should be very bright, relatively, okay, brighter. If I am in a model with omega matter 0.3 rest curvature, they should be fainter. And if instead of curvature I have cosmological constant, they should be even fainter. Now you can actually observe the supernova and you find that they correspond to the third case. So they appear fainter than what they would have appeared if I were in any of these other two models. Okay, so we need something to increase for the same redshift, we have to increase the distance to the supernova. Okay, and one way to do that, the only way known to do that presently, okay, one of the ways known is to introduce such a term which has negative pressure. Okay. So now the question, and this is this unknown quantity which has an energy density rho lambda and which has a pressure this we have discussed that it should be less than minus 1/3, right. So this quantity, something like this is required. What this will do is it will increase the distances as a function of redshift. Okay. Now the question is, what is this quantity which has negative pressure which fills the whole universe? Now there are three possibilities, or what is the quantity? Essentially you want something in the dynamics of the universe which will increase the luminosity distance predicted. At the same redshift, you want to increase the luminosity distance that is predicted. Okay, redshift is fixed, you have observed a supernova. You take a model with only matter, you get some luminosity distance. It turns out that that luminosity distance is too short. The supernova are fainter than what you predict. So then you want to increase the luminosity distance. How will you do that? You reduce the matter, it will increase but not sufficient. So you want to increase it even further. And this can be done by introducing some constituent of the universe which has negative pressure. Essentially it boils down to this. Okay. Now one possibility is the cosmological constant. So this thing that you introduce is called dark energy. The cosmological constant is a possibility. The cosmological constant is a term that is admitted, it is a constant that is admitted in Einstein's theory of general relativity. Okay, it allows the existence of such a term, and it is a constant of nature then. Okay, or it is a constant which is determined by some physical mechanism, it need not be a constant, but the way Einstein thought of it, it was just a constant of nature. Okay, just a constant, which how it arises again a different issue, but there in that picture it is a constant. Okay, and that constant has the property that if you think of it as a fluid, W is minus 1. Okay, that constant has a property, if I think of it as a fluid, then W is minus 1. Another possibility that has been, I am just discussing some of the possibilities which people have considered. There are various other possibilities, it is an open issue, right. So you can come up with the possibility yourself, and then the thing would be then to put it in the theory and test it against the supernova data. So people have considered a large variety of possibilities, I am discussing just a few of them. Another possibility goes by the name of quintessence. This is a dynamical cosmological fluid. The cosmological constant is a constant, there is no dynamics to it, right. Now people have proposed another possibility, considered another possibility, that is called quintessence. It is a dynamical cosmological fluid which has got negative pressure. Okay, and you can have different ways of realizing such a thing. You could have a scalar field with a particular potential, and there are various other ways in which you could realize it. So, it is a fluid. Okay, the cosmological constant is really not a fluid, it is a constant in the theory, a constant of nature, okay, if it is there, or it is a constant in the theory which essentially is a constant of nature. Now, quintessence is a fluid, so you should really think of it as a fluid that fills the whole universe. It is a dynamical fluid, so it has a dynamics. As the universe expands, it changes, its properties change, and it has a negative pressure. These are the properties you would like it to have. Okay, and the W over there is not necessarily 1. It could be some other value. It has to be less than minus 1/3 if it has to explain these observations, and the W itself could be a function of redshift. Another possibility is that Einstein, so both of these possibilities are based on the Einstein's theory, general theory of relativity, okay, the theory of gravity, known theory of gravity. Now, there is a third possibility which people are also considering, and this possibility is that the Einstein's theory of relativity, general relativity, the theory of gravitation, is incorrect. Maybe there are modifications on large scales, okay. And one of the possibilities that people are considering quite seriously is that there are higher dimensions. There is a, so we really are not living in a 4-dimensional space time, but there is one more extra spatial dimension which is extremely small, okay, and that could also produce some kind of an acceleration. So, this is an active area of research determining what the dark energy is, and to do this one has to measure which curve we are in, these curves, to greater levels of precision. So, there are several ongoing projects and future projects. I will just show you some of them over here. So, these three are aimed at probing different redshift ranges, okay, and there is a satellite project SNAP which is planned, which will probe the entire redshift range up to redshifts of roughly 2, less than 2. So, these are ground based, using ground based telescopes, supernova searches, and this is a satellite which is planned in the future, and they will probe different parts of the redshift range. The satellite will probe the entire redshift range up to here. This shows you a visualization of the satellite that is planned, supernova acceleration probe, and the main aim of this satellite is to determine what the dark energy is. It's a big, it's an enormous this effort that is going on towards determining what this dark energy is. It's an unknown thing in our universe that is causing it to accelerate, very mysterious. So, this shows you some data from SNAP, from ESSENCE. SNAP is yet to be launched. So, I had shown you 3, these are already possibly functioning, okay. This is a very fast changing field. So, the data I have been showing you is not the latest story, okay. This is a rapidly evolving field, intense research going on. So, this shows you some results from ESSENCE, one of the projects. So, they are aimed at getting more and more supernova data which will reduce the errors. And the question that people are addressing now is, what is the value of this W? If W is exactly -1, then you more or less know that it is a cosmological constant, but if W has a value which is different from -1, then you know that it is not a cosmological constant, okay. It is something else, and if you can then look at the redshift evolution of W, that will give you more information about what it is. So, people are, what this picture shows you is the parameter W and omega matter, okay. Omega lambda is now value is taken, fixed, okay, and this shows you W and omega matter, and there are a variety of observations that have gone in. There is something called the baryon acoustic oscillation which I have not discussed till now, and then there is the supernova data, and variety of other observations that have gone in, and okay, these are the only 2 observations that have gone in, and it seems to tell us that W has a value which is very close to -1, indicating that it is possibly a cosmological constant. But again, this is some area where there is intense research going on, so we really do not have the last word as yet. Okay. Now, before we finish, there are a few things which I have not told you, which I should tell you. There are questions about using supernova as distance indicators. So, what we find is that the flux from the supernova is less than what is predicted in a model without a cosmological constant, without dark energy, right? That is what we observe. Now, it may be that there is some dust, there are particles, dust I have told you are particles, I have already introduced dust, right? They absorb light in our own galaxy, which had created problems right in the beginning when people try to determine the shape of our galaxy, the size of our galaxy. So, there may be dust which is causing the supernova to appear fainter. Okay. Maybe the properties of high redshift supernova are different from the properties of the local supernova. So, these are questions which, and people have more or less figured out the answers also, and people are quite confident that the supernovas actually are good distance estimators. These effects are not very significant. But again, I should tell you that before I close, that this is a field of ongoing research. So, I will urge you to look at the latest literature and get a feel for what is going on yourself. Okay, so let me stop here for today.